Hello everyone, good morning, good afternoon, good evening. Thank you so much for joining us today. My name is Caroline Maître and I will be your webinar host coming to you from Paris. Today's webinar topic, we will be looking at eliminating aerospace certification gaps utilizing the electrical system digital twin, explore analysis tools to leverage the electrical system digital twin. I am delighted to welcome as our speakers today Mr. Steve Caravella, Mr. Colt Breck, and Mrs. Madison Case. I will leave now Steve Caravella to present themselves and to kick off this webinar.
Hello, and welcome everyone to our discussion today about eliminating aerospace certification gaps utilizing the electrical systems digital twin. This is Steve Caravella, and I work as Market Development Manager for Siemens Digital Industries Software with focus on the aerospace and defense industries. I have 28 years of experience in the aerospace industry working at aircraft OEMs with expertise in areas of engineering design, certification, and project management. During that time, I did engineering design and led engineering and certification teams in development of new products, sustaining products in production, aircraft outfitting, modification and retrofit, and on special missions projects. Joining me today are Colt Breck and Madison Case, who will be talking about some of the ways the digital twin can be utilized in eliminating certification gaps. I'll have them give a brief introduction before we get started.
Hi, my name is Colt Breck, and I'm a pre-sales solutions consultant for Siemens PLM. I've been with Siemens for 2 years and have 5.5 years of industry experience using capital across automotive, aerospace, and spacecraft programs.
Hello, everyone. As Steve stated, my name is Madison Case, and I've worked as a pre-sales solutions consultant for the Capital Tool software in the aerospace and defense industry for just over 3 years. My background originated in mechanical engineering, but I've since shifted my focus to wiring and harness design.
Okay, thanks guys. Let's start off by recognizing 4 key trends in aerospace and defense today. First, the industry is undergoing a tremendous amount of change. Many aerospace programs are either over budget, late, or both. The pressure to reduce program cost and schedule while meeting requirements is one of the big challenges. At the same time, aerospace programs are becoming increasingly complex and highly integrated. As companies seek to improve their product performance, reduce weight, or provide more functionality, they seek integrated solutions and are relying on more software. This increased complexity creates challenges in certifying new products and bringing them to market quickly. We're also seeing more electrification of products. Some of this is driven by the desire for greener solutions. Some is driven by increased automation or autonomous vehicles that increase demand for software. And some companies are replacing mechanical systems such as hydraulics with electrical systems to improve reliability and maintainability. Finally, there is increasing global regulatory oversight. Major efforts over the past decade to delegate authority to OEMs have been progressing, but not at the pace desired by industry. Recent high-profile events have not only raised public attention to product safety, but have also caused regulatory agencies to increase direct involvement in certification activities. Companies need to get ahead of this, and one way to do this is to complete design validation earlier in the development process. This can be onerous and time-consuming, but there is hope. One step companies are taking is going digital with product design and carrying that through the value stream. Today, we're going to look at areas where this effort can be extended to help eliminate gaps in the certification process. To orient us on our discussion today, let's start by taking a high-level look at the design, build, and certification process. As we set out to develop or customize products for a given market, we start with an idea and the goal to build and deliver the product. Most of us tend to think about the design process, which in simple terms begins with requirements definition, architecture, and preliminary design. As the design matures, we move into detailed design of wiring, harnesses, and installations. This then moves into procurement, fabrication, and final assembly. We know there's a requirement to certify the product design, and this process flows alongside the design process. Certification begins with engagement of the regulatory agencies to establish requirements. As the design is maturing, we perform analysis and conduct testing to show the design meets regulations and generate numerous reports. Following final review and approval by the regulatory agency, we receive type certification of the design. However, the reality is not so smooth and simple. Historically, The engineering approach has included some basic analysis during the engineering design, but full and comprehensive certification analysis happens after engineering release when material procurement and fabrication is already underway. There is a gap here in that analysis is usually done with disconnected tools such as Excel, spreadsheets, MATLAB, or in-house developed programs, which require manual review of the data, manual data input, and review and verification. When analysis finds deficiency in the design, a design change is required. This creates a ripple effect through the procurement and manufacturing flow, as well as an iteration in the analysis and reports. Even worse, if something is missed during the analysis process, it will be found during certification review. This creates a critical situation for an urgent design correction and likely rework to already manufactured process. This separation between design activity and analysis activity is one of the critical gaps in the certification process. One way we address this at Siemens is to digitally integrate analysis tools with the design tools. Integrating design tools with analysis tools starts with the configuration-controlled digital twin to provide accurate information describing each product configuration. Remember, the digital twin is more than just engineering in CAD. It is a true model-based digital representation of the product design. Using the digital twin, we can create compliant designs of the electrical system from the beginning by using rule-based verification and constraint-driven design. Automation enables continuous validation of design compliance by interrogating an authoritative model of the product's electrical system. This allows design and analysis engineers to check, analyze, and integrate the design and address concerns immediately. Now I'm going to hand this over to Colt and Madison to show some examples of what can be done.
So let's take a look at how we can accelerate certification using Capital. So when we think about compliance requirements, we're really thinking about a couple different things here, and one of them being electrical load analysis, and the other being EWIS requirements. Now with Capital, we can complete electrical load analysis early on in the program. It's free for engineers. It's going to help drive correct by design construction by using live data and leveraging information that we've already input into our design process. And then for EWIS requirements, we're going to be able to drive signal separation through some design rules and constraints and prevent rework at the end of the program and help avoid end of program redesigns for certification. So we'll also be able to do things like drive certified parts into our designs or the entire vehicle platform all at once. So when we take a look at electrical load analysis, let's go ahead and look at the traditional load analysis method. Typically, you'd have somebody who would manually go out and collect information from designs, take that information, load it into a spreadsheet in something like Excel or some other kind of homegrown database. They would then take that information and they would lay out a visual representation of the power architecture through what we call the single line wiring bus diagram. Typically, this is done in something like Visio or some other kind of drafting tool. Once all that information is done, then the engineer can run bus and source load analysis. Usually this is done via some kind of macros or equations all loaded into your Excel spreadsheet and so forth. And then once you've verified the analysis looks correct, then an engineer can go ahead and create some kind of publication in either a Word document, or it can be an exportable macro from Excel or some kind of other PDF editor. And what it ultimately leads to is a very labor-intensive process. It's very error-prone because you're looking at dual or triple or maybe even quadruple documentation. It's late-stage analysis. This is more of a batch process done at the end, and it's all very manual. So then all these tools are disconnected. So what we want to be able to provide is something a little more automated. We want to extract the data that's already being put into a program and reuse it. So what we're offering with Capital is you're already doing all this design in what we call logic. You're doing all your wiring design, your schematic design, your block diagram, and all that stuff. And we want to just reuse that information, and we want to stay connected and be able to run analysis live. And then we also want to be able to create our single line wiring diagram in the same environment and reusing those same live parts. And that is something that Capital Logic will allow us to do. We'll also be able to run on-demand load and source analysis inside Capital via the ribbon and the ELA license. So we'll be able to do things like bus load analysis, source utilization analysis, battery analysis, all on the fly at any time during the design process. So this will really eliminate end of design risk and program scheduling. And then also in Capital, we have another tool inside the suite, which is a publications tool. And so we'll be able to do on-demand report generation with live data. And so we can build this report out as we go. Ultimately, what it leads to is a correct by design philosophy. You're going to have a reduction in human error because you're not double documenting or triple documenting the same thing over and over. You're going to be able to leverage on-demand analysis and on-demand report generation. So the ELA data flow inside Capital will look like this. First, you're going to have what's called configuration management. You want to be able to run your analysis tools on a particular tail number or configuration, and we can do that through scoping and build lists inside of Capital. We'll then go ahead and create our single line diagram by reusing existing devices and components inside of Capital that we've already loaded into our wiring designs. We can then do some data management through the built-in GUI for the ELA tool itself. We can enter in different parameters for the loads, for the power sources. We can also define the flight schedule for the plane, G1 through G5, G1 through G10, whatever that is, engine startup, taxiing, cruising, takeoff and landing, and all that stuff. We can then run analysis verification on all the different types of, on all our buses or all of our sources, and make sure that we're getting the numbers that we're expecting. Then we can do some report authoring through the ELA report builder inside of Capital Logic. So you'll be able to adjust the look and feel of your actual output report. And then we can publish through Capital Publisher and actually spit out a report in seconds or even minutes. So when we look at configuration management specifically for ELA, we do scoping through what we call build lists. And all it is a collection of designs with relation to a specific configuration or tail number. It's going to help the engineer organize designs into different configurations. You can easily toggle between different tails and choose which ones you want to analyze. It makes it really easy for the user and so forth. So then once we have our build list set or our scope, we can go in and create this single line bus wiring diagram. And all it is a visual power architecture representation. And so what we're able to do though is reuse the data that's already been input into our wiring designs or what we call our underlying designs. So our power architecture is going to consist of our power sources, our buses, our switching architecture, batteries, and we don't need to show our loads or anything in here because that's all connected through the build list management, the collection of designs. And this is fully customizable. The look and feel of it can be totally whatever the user wants it to be. In this particular example, we're showing AC in red, DC in green, and so forth. Now, the data management is also very easy inside of this tool. So at the click of a button, we can pull up this data manager. And what this is going to allow is the user to input different parameters for different sources, for different loads. You're going to be able to edit the flight schedule. You're going to be able to edit which loads are on during different flight phases and so forth. So if we look at how to, if you look back here, you have this button down there called Edit Airplane. And what it's going to allow the user to do is define different flight phases for the particular aircraft. This one's going to have an engine start, it's going to have a climb, it's going to have a cruise, landing, and then a taxi phase. And so through the push of the button, you're going to get this, and you can edit different parameters within each flight phase as well too, as far as airspeed, altitude, and so forth. Once you have your flight schedule defined, then you can go further and define different types of loads that are turned on during that flight schedule. So let's say during G1, the engine start, we have our turbine and lights going. And then maybe when we move into our climb phase, we turn on some music, and then we go into our cruise, and then we also turn our radar on. And then once we come back into our landing phase, we turn the music off. And then during taxi, we can go ahead and kick our radar off at that point. So you can define all these different parameters within the valid flight schedule editor just by simply putting a check mark during which flight phase they're turned on, and then you can adjust their ratings at different intervals. And the different intervals are 5 seconds, 5 minutes, and continuous power. So now, after we do our data management, we can go and run analysis verification also at the click of a button anytime in the design process. And depending on which type of component you have highlighted when you run this analysis, Capital will know if you want to run source utilization or bus load analysis or maybe battery analysis. This is an example of what source utilization analysis would look like. Again, everything in green is editable, so a user can come in here and define shaft RPM and stuff like that at different flight phases as well and see the effects of that change. This is what a bus load analysis look like. So if I had a bus selected when I run this action, it'll show me the different connected loads that are connected to this particular bus. Then also in the load analysis tab, it'll show you how that particular load affects each flight phase of the flight schedule. Then you also have a battery analysis. And in here, you can define different discharging patterns for loads at different flight phases. And we'll take a little bit more look at that. So by running analysis on a battery, you're going to get this menu. Again, everything in green is editable. So you can go in here and edit discharging patterns for loads. And then once you do all of that, you'll be able to see your battery capacity at different flight phases, depending on the loads and their discharging patterns. And it's very visually easy to see. So now that we've gone ahead and verified our analysis, everything looks the way we want it to. We want to go ahead and create a report. Well, before we actually publish a report, we want to go ahead and author the template. So in here, inside of Logic, we have this ELA report builder. It's made up of chapters and then contents within those chapters. So in here we have, let's see, 1, 2, 3, 4, 5, 6 different chapters. And if you click edit, you get this HTML-based editor. You can do things like simple text, sizes. You can do bold, italic, all those typical functions you'd find in like a Word or Notes editor. But we also leverage what's called tagging. So everything in blue here is actually calling out information in our underlying designs. So the first one's calling out a design property. Well, the first 3 are, and then you can also call out a report name, block range, and so forth. And we'll see what that looks like in a report here in some upcoming slides. But basically, with tagging, what we're doing is we're leveraging live data again, so that we don't have to manually come back in and update that later. Also, with a report builder, once you get the look and feel you think you like, you can export that template and save it off in a local directory somewhere. You can pull that template back in at any time. You can pull in just individual chapters of a template as well. So if you like chapters from one template, and then maybe you like the chapters from a different template, you can merge those two together and create a new one, and so forth. So it's very drag and drop and easy to use. Now, once we have the report builder finished and populated, we can then generate the report. And so we use what's called Capital Publisher. We can open this. We can select our ELA packager, select our scope or our configuration or our tail number. And then all we do is hit create package. It's very simple. You click the button and it spits out a report based on your template that you have set. So in here you see that we're automatically pulling in our document number or revision, our release date. All that information is live and it belongs to the designs themselves. So we're not coming in here and manually selecting and retyping anything at all. And so another thing we want to talk about is some EWIS compliance and how we can use Capital to drive some of those requirements. So we have a tool called Topology, and it provides a top-level view of our vehicle. In here we have this helicopter, and what we can do is we can define some rules and constraints. Rules are just a collection of constraints. So in this particular example, we're defining along certain route paths. Do not route conductors with a EMC category of FC or data. And then on another bundle route, we don't want to route anything that is secondary. So we want to keep that to primary only. So we can use this tool to do some automatic routing for us based on requirements set by the user. So we can apply these constraints, and then Capital will automatically route everything based on the rules set forth by the user. So it'll route primary and secondary individually and separately. It'll also separate different EMC categories defined by the user. So it's very quick, very efficient way of doing vehicle-wide harnessing. We can also drive certified parts. So we always want to ensure we're using certified parts, to comply with UWIS and the FAA. So what we can do is, in this example, we're going to drive some part numbers based on FAR's Part 25 rules. And here in this particular example, we're going to drive some wire specs based on that rule. So if we have different EMC categories, use this part number. If we have flight controls or DC or ground DC or data, then use so-and-so part number. And so we can set those rules up, and then all we have to do is apply our constraints, and it will literally apply that rule to every single thing on the entire platform. But you can also run this at the design level as well. So if you don't want to override anything that somebody else has done, if you have multiple users working on different designs, they can run these rules and constraints on their designs only. So what it's going to help you to do is validate UWIS compliance early on in your design lifecycle, and you don't even have to worry about it at the end to ensure or make sure users are using certified parts.
As we're all aware, managing configurations of designs and assigning different revisions to certain effectivity ranges can become increasingly complex. With the correct configuration management tools, we can start eliminating this gap. What we're looking at here is a very simple example of having 3 designs, each with 2 revisions, and these designs are assigned to 4 different tail numbers. However, each tail number is assigned to different configurations of the designs. Imagine now we have, let's say, 5 to 6 revisions per design on a run of 100 tails. How are you going to tell the FAA what designs were used to produce what tail? In this case, we want to know which designs are applicable to tail C. So before, we'd have to manually track this information and hope we didn't miss a revision or forget to update any configurations. It was a very manual and error-prone process. Now we can automatically track configurations, and we can choose which tail or effectivity range we're interested in, and all applicable designs will be pulled for us. So we can take another look at this concept, but in terms of design revisions versus tail numbers. So here we have one design with 4 different revisions. Each of these revisions is tied to a different series of tail numbers. Instead of looking at which designs belong to each tail, we have the ability to view all of the designs applicable to a single design revision. So it's important to note here that even if we're changing the effectivity range of a certain design revision, we're not actually making any changes to that design itself. So this provides us an interactive way to view, edit, and verify that each revision is correctly applied to a tail number. So simply put, Capital provides automatic identification of unique configurations based on effectivity. Although Colt touched base on the use of build lists earlier in terms of ELA configurations, we're going to look at the power of a build list in relation to aircraft builds. A typical aircraft will be made up of several key systems, each containing hundreds of lower-level designs. The method used to organize this design content is through build lists. So these build lists identify a number of designs that are used to construct any given build. This could be subsystem, major system, or even an entire aircraft. So as revisions are added, Capital automatically tracks which effectivity level the revision is applicable to, which ensures correct application of designs, eliminating any gaps in managing configurations. So let's say, for example, we need to pull all designs for tail 001. We can create a build list, assign it an effectivity of 001, and then all of the designs will be pulled for us, and we can report out on that list. So now we're going to pop into the tool itself and see how this works. So as you can see here, we're going to be focusing on wiring design DC power. Within this design, we have two revisions, revision A and revision dash. So if we take a look at the effectivity assigned to revision dash, we notice that it is applicable to build S41 as well as S476 through 9,999. Popping into revision A, we can do the same thing. We notice that this effectivity is applicable to tails 2 through 75. We have the ability to go in here and add additional effectivity. So let's say S4 1000 to S4 1001. So changing that effectivity is not actually changing the design itself. We're just adding additional information to that design revision. In terms of build lists, we can right click and choose create from effectivity. Let's say we are interested in effectivity 70. So we choose that and choose OK. This is going to automatically pull all of the designs that are assigned to the effectivity 70. So this eliminates the need to manually go through all of our designs and their revisions to pull the applicable designs for tail number 70. So with the amount of design changes and increasing complexity, how do we ensure our data is coherent? This is where change management plays a big role. So it's typical to have designs change as the aircraft matures. However, there's often a lag time between changes being made and stakeholders understanding what these changes are. So for example, we've created a revision 1, but then mechanical comes to us and says that there needs to be rerouting done, so we then create revision 2. As the design is evolving, we want to see what these changes are. So to understand what changes have been made between revisions 1 and 2, we can use the Publisher tool to generate a report. This aids in answering questions such as, what would cause this change to be made and how do I get value out of that information? Traditionally, we would need to sit down with both designs side by side and decipher any differences. But with Publisher, we can auto-populate the design changes and even make this report available to stakeholders outside of the Capital environment. So by validating ECOs, this tool can be used by many teams such as materials, manufacturing, or a DER to accelerate the acceptance process and getting us one step closer to that validation. So let's take a look at how this works in the tool itself. So what we're looking at here is a change illustrator package created from our Capital Publisher tool. We have our revision dash and our revision A, and we can look at what the design changes are between the two. On this left side here, we have different reports which can be configurable and customized. So we can start at the summary report here. All of the items in red means that they have been removed, green means that they've been added, and then yellow means that they've been modified. So if we look here under the Objects Removed tab, we can click on these hyperlinks and it directs you to that object. We can also do the same for the objects added. Click on that hyperlink and it will pop you into the object in question. In terms of objects modified, these are also hyperlinked, and we can see that the change here has been a part number from a 22-6 to a 24-9. So all of these reports provide us different information on design changes between these two revisions. We also have the ability to export this as an Excel file. What this does is it gives us the ability to send this information to users and stakeholders outside of that Capital design environment. Both configuration management and change management play a role in eliminating certification gaps. Through the use of build lists and automated report generation, we have the ability to quickly and accurately report out design changes and the applicability of designs. And with that, I want to say thank you for joining our discussion today on filling those gaps in certification in the aerospace industry.
I would like to thank again our presenters and experts today, Mr. Steve Caravella, Mr. Colt Breck, and Ms. Madison Case. And thank you all for joining and for your interest in Siemens Global webinars. With that, the session is now closed. Goodbye.